Right, let's get started. Welcome everyone to the colloquium. My name is Sebastian Will. I'm an experimentalist from Columbia University working on ultra-cold atoms and molecules. It's my great honor to introduce our speaker, our colloquium speaker today. We are very excited to have Marianna Safronova with us today at the Aspen colloquium. Marianna is a professor of physics at the University of Delaware and also an adjunct fellow at NIST, the Joint Quantum Institute, JQI, and the University of Maryland. Marianna is a theoretical AMO physicist, so I'm only remotely qualified to talk about her work. But she also works in close exchange with experimentalists. So Marianna's research focuses on searches for new physics beyond the standard model, including searches for dark matter and variations of fundamental constants. So to drive these searches forward, she is performing calculations on the structure and properties of atomic and molecular systems. With these calculations, she identifies the sensitivity of energy levels in atoms and molecules to known and perhaps unknown physical effects. As an example, Marianna has done groundbreaking work in the area of atomic clocks. Her work has been instrumental in understanding and reducing systematic effects in atomic clocks, making them more precise and making them, in fact, one of the most precise measurement devices humanity has available today. Today these atomic clocks are so precise that they are not only good for timekeeping, but there is hope to use them for studies beyond atomic physics, reaching into high energy physics and astrophysics. Recent years, her research has driven forward progress in nuclear and molecular clocks as well. And Marianna is truly an interdisciplinary researcher and really crossing borders. So, Marianna received her PhD at the University of Notre Dame in 2001 with a thesis entitled High Precision Calculations of Atomic Properties and Parity Non-Conservation in Systems with One Valence Electron. So that really set the theme for her, all the research that followed. And besides her, and then after a brief postdoctoral stint at NIST in Gaithersburg, she moved on 2003 already to University of Delaware, where she has been ever since. So besides her groundbreaking research, one really needs to mention Marianna is a true integrator for the whole field of AMO physics. There is, almost no experimental group in AMO physics that has not worked with her. And as a testimony for the quality of her work, I'm going to quote Luis Orozco, a colleague of us in AMO physics, who once shared in his talk, "You should never bet against Marianna. Her calculations are always correct." So she's extremely highly respected, obviously, in the community. Of course, she's an APS fellow. Marianna's importance to the community also becomes clear through her service to the community. So the list of things she has done is actually endless. I just mentioned a few examples. She has been the chair of the APS DAMOP division. She has been a member of the decanal report on AMO science, the National Academy of Science. She's currently the chair of the NASA Fundamental Physics Program Analysis Group. And she has been a member of the Physical Sciences Panel for the Decanal Survey on Physical Science Research in Space. So clearly her interests are shifting from earthly labs, striving towards space. And I'm sure we'll hear a lot more about this today. So Marianna, we are very happy to have you here for the colloquium. The floor is yours.
Thank you so much for a great introduction, and it's great to be in Aspen again and now give a colloquium. 100 years ago, we didn't know what atoms were made of. And they have been puzzles. Just as we have today, those are puzzles of 100 years ago. The photoelectric effect, the atomic spectra, the Stern-Gerlach experiment, which just people shed some light on what's actually happening in their year before 1924. And when we solved those fundamental physics puzzles, like atomic spectra, it's one of the most literally unapplied fundamental things you can think of 100 years ago, we got quantum mechanics. And from quantum mechanics, we got many devices. Our essentially fundamental technology now depends on quantum mechanics. And no one had any idea 100 years ago what we would have now. Even with the invention of lasers, people have no idea how those actually would be used. And now, extending from using quantum mechanics to controlling quantum system, the atomic, molecular, and optical physics now is capable of making atoms or molecules ultra cold. You can literally trap a single atom and stop it. And then, now, since those are ultra cold, they can be trapped. And when they can be trapped, they can be precisely controlled. Why actually do they need to be ultra cold? Because all of those traps, especially for neutral atoms, those are Stark shifts. Those are very, very small trapping potentials. So to stop them, they need to be first laser cooled or cooled by very sympathetic or other means. And now, when we have them trapped, we can actually put them in specific superpositions, entangle them, and manipulate with them. And then we can do precision measurements to the level that our fundamental physics postulates have not even been tested at those levels. And that brings us to quantum sensors. So the reason why we talk about the quantum devices and specifically AMO quantum sensing is because we can now precisely control individual quantum systems. And of course, people ask us, well, what's a quantum sensor? What requirements does device should satisfy to be qualified as a quantum sensor? And me and Dima Butker put together a focus issue a while ago, quantum sensors for new physics discoveries. This is really a forward-looking issue of 20 R&D and future proposals for things like dark matter searches, looking for violations of Lorentz invariance, and those many, many interesting things. We decided to write an editorial, and I'm proud that's the only paper which arXiv rejected, which I've submitted. I think the word elephants is like big elephants in a room, like dark matter, dark energy, seem to have they have a problem with. So we decided we'll take a broad view. So any technology which requires quantum mechanics to describe it, we'll call quantum. And then any device, measurement or sensing capabilities of which are enabled by our ability to manipulate and read out as quantum state, we will call a quantum sensor. Why? Well, we tried it out. Spectrometer is not a quantum sensor by this device. You read out, but you don't manipulate the state. But atomic magnetometer or atomic clock is, because you put your system in a certain state, you let it evolve, and then you read this out. So that's in which sense I use the word quantum sensor. That pretty much makes all of our new beautiful atomic clock sensoring devices quantum sensors, atomic clocks, interferometers, magnetometers, levitated nanoparticles, and many of those atomic molecular experiments. Many of those molecular experiments are discussed here at our ultra cold molecular workshop. We actually make them using quantum sensors. Now, we have new puzzles. We have found all the particles of what's called the standard model. In standard model, quantum mechanics and general relativity have been tremendously successful. Those are things which have predictive capability, gold standard of theories. They describe experiments which we do on Earth, they describe many phenomena, and they've been tested to extraordinary precision. The only problem with the standard model that if that was true, we would not exist. Because somewhere in the early universe, the amount of matter and antimatter which was produced differed. Because in standard models, there is a little bit what's called a CP violation, charge parity violation, but very little of it, not enough to end up with galaxies full of matter. Because if you produce matter and antimatter in nearly the same quantities, then eventually they annihilate and you essentially have your radiation dominant universe, which clearly didn't happen just because, well, we're sitting here in a beautiful Aspen and enjoying our scientific discussions. And of course, there are those big elephants in the room. We went from that we didn't know what atoms were made of, that we don't know what universe is made of. We know what it's not made of, and it's not standard model. So the standard model contributes only about 4.5% to the total matter energy composition of the universe. And then, of course, there are other things which standard model has problem with. There is no mechanism for neutrino masses. And as I've mentioned, the dark energy, it's a fact that universe expansion rates seem to be accelerating, which is not explained by a standard model. And those are the reasons why we need physics beyond the standard model. We are not talking about a couple of sigmas here and 2 and 5 sigmas here. We are talking about serious problems just as we had 100 years ago. When 100 years ago, people had mechanics and thermodynamics and electricity and magnetism, and they understood how things work. But there were puzzles they did not. And now, you go back full circle. So in 1925, we had this fundamental physics puzzle, solving which gave us quantum mechanics. Now, quantum mechanics gave us quantum sensors, and hopefully now, they will allow us to help solve fundamental physics problem of our time, in addition, of course, to those magnificent particle physics and astrophysics and other experiments and observations. About a few years now, more than already 7 years ago, we decided to put together a review on the search for new physics with atoms and molecules. And we decided that we are going to have it as a single review. And this is a large area. So we start from, of course, precision test of quantum electrodynamics. That's, was essentially starting point to developing field theory, was a lamp shift, the QED. And now, of course, we're still continuing those tests, but now we have many, many different other things we actually do with atoms and molecules. And at this point, reviews of modern physics, actually, we were specifically discussed at the board meeting that allows us to exceed the normal limit by a factor of 2. There are 1,100 references, and the field was so rapidly expanding, we had to put